Okay, so let me attack lecture 2. The idea this time is more to work on actual statistics of turbulent flow, with a focus on homogeneous isotropic turbulence. So these hydrogen atoms of physicists of turbulence, and to show you some exact results which exist, and how this relates to the scaling laws we discussed yesterday. And then I will talk about intermittency and anomalous scaling in turbulent flow. So basically, so this is just a small recap on Kolmogorov 1941 that we have seen yesterday. So you remember that one of the main aspects of the description of turbulent flow is the fact that there is a constant flux of energy from the large scale to the small scale. And this flux of energy is equal to the rate of energy dissipation, of kinetic energy dissipation, and it's given by this formula. So basically like the square gradient times the viscosity, and this is average over space and realizations of the flow. Okay, so now the ideas that we developed in order to get these ideas of a scale-dependent turbulent flow was to consider something which was representing the amplitude of velocities at a given scale L, and we introduced this scale-dependent Reynolds number, okay, which was depending on this velocity. And then what we said is that we are in a turbulent flow when we consider scales, so sufficient large scales, so that this local Reynolds number is very large. And then we had a cutoff scale, which was the Kolmogorov dissipative scale, at which this guy is becoming of the order of unity. So inside the inertial range, so which is defined as scales which are much larger than this dissipative scale and much less than the scale at which we are injecting energy. So what the essence of what we said is that the statistics are only depending on the transfer rate, so or the dissipation rate, if you want, and on the scale at which we are observing our velocities. And this was leading just through a dimensional argument to say that the typical velocity will scale like epsilon times L to the power 1/3. So this is Kolmogorov 1941 approach. Okay. And then, so we have this cutoff scale at small scales, which is the Kolmogorov dissipative scales that I denote eta, which is defined as the place where this scale-dependent Reynolds number is equal to unity, and this gives you this dissipative scale as a function of viscosity and energy input or energy rate, and you remember that when we make viscosity to 0, we have that this scale is going to 0 also. Okay, so now, so basically this is somehow the phenomenology. So now there are some arguments which are trying to address in a theoretical manner this phenomenology. So in order to formalize a bit, so instead of thinking about this typical velocity at a given scale, so what people are usually considering are what are called velocity increments, so, okay, which are defined as the velocity difference over a given distance L, over a given separation with a strength L. Okay, so you can see it this way. So you take 2 points, x and x plus L. So L is a vector, and now you have 2 velocities at these 2 points, and you look at the difference between these 2 velocities, and of course you can project it both on the longitudinal direction, so on the direction which is parallel to the separation between the 2 points, and on the transverse direction. So you have these 2 transverse and inverse and longitudinal and transverse components of the velocity increment. And then the question that is behind this is to try to understand how the probability density, so the probability distribution of this velocity increment, condition on space, the length scale, and time is behaving. Okay, so that's more or less what we want to describe in order to describe the kinematics of these turbulent flows. So in homogeneous and isotropic turbulence, so basically we can clearly use isotropy and homogeneity to get rid, and stationarity in time, to get rid of the x dependence, of the time dependence, and to project delta U on the separation L. So that at the end, this thing which was depending on 3 plus 3 plus 3 plus 1 variables now depends only on 3 variables. Okay, so one is the longitudinal increment, so the increment, the difference of velocity projected along the separation vector L. The other one is the modulus of the remaining part of this velocity difference, so which is a transverse increment. And of course, the separation now is just a scalar. Okay, so longitudinal and transverse are defined this way. So now, how in this language we can reformulate Kolmogorov 1941 phenomenology or similarity? So the fact that the velocities are typically scaling this way as a function of L means that we expect such a scaling form for the probability distribution, the joint probability distribution of longitudinal transverse increments at a given scale L. So basically a scaling function. So this is just the normalization factor times the scaling functions where the velocity differences are just rescaled by this epsilon L to the power 1/3. Okay, so that's just the way to formalize a bit K41. So now the one object that people are looking at are what are called structure functions. So what are structure functions? And basically, they are just the moments, so the p order moments of these velocity increments. Okay, so you can talk about the longitudinal structure functions or the transverse structure functions, depending on, or you can have mixed structure functions, depending on what kind of quantity of interest you're willing to look at. And so there are 2 exact laws, again, due to Kolmogorov, which are ruling some moments of these increments. So the first one is a direct consequence of isotropy. And this consequence of isotropy is giving you a relationship. So you see it's a differential relationship between the longitudinal increment and the transverse increment. So this is just a consequence of isotropy. Then there is this relationship is a bit trivial, but there is another relationship. So which is
Jeremie, I don't see how it follows this relation from isotropy.
So this one.
Yeah.
So basically, you just have to put some. So you have to write things. So you can think about writing the full tensorial form of the increment. Of the second order correlations of increments, and then you assuming isotropy, this gives you so you decompose it as an isotropic tensor, and then you project the perpendicular and the parallel parts. I mean that's just manipulation of isotropic tensors and isotropic decomposition of tensors. So there is nothing magical there. You don't need Navier-Stokes. No, they are not independent from each other. They are not. They are not independent. Exactly. Yes, and it's evolving as a vector. Okay, so basically this thing is just a consequence of isotropy. I mean, there is no need to plug Navier-Stokes dynamics in it. The second relation, yes. I'm sorry. Exactly. So you can write. So you can write somehow. You can write something like delta ui delta uj. Okay. So which will be a second order tensor. Then you this thing depends on the vector, which is the separation. So you write the isotropic form for that, and then you contract to get the longitudinal and the transverse part of this thing. And this is giving you a relationship between the coefficients that are known, that are functions of just the scale, and this relationship between the coefficients are giving you this equation. That's all.
It means that this function psi, right, in the previous one, the scaling function of the probability.
Yes. So
it should satisfy some relation.
Exactly.
Right?
So this is one of the relationships that has satisfied.
And that's
so basically,
not,
it's, if you want, this is the relationship between the second order moment of the marginal
So
with respect.
How does one derive this? Like from the, if I start with the probability distribution?
No, you don't. No. So basically, so what you write is instead of parallel and perpendicular, you write something like you introduce some Dij of your vector L, okay, that you define as being the I component of your increments, which depends on L, times the J component. Okay, and then you use isotropy to say that this should be a second order tensor, which depends on a vector. So I don't remember. I don't want to write it down. So you will have some. I guess that you will get some terms which are like proportional to delta ij, and other which are like Li times Lj. Okay, so I guess that you have two functions. Certainly, it will be something like this. So a function which depends only on the length, and another function which depends only on the length times that. I guess this will be the decomposition. And now, so this is a consequence. The fact that you can write this way is a consequence of isotropic statistics. And then you project properly the I and the J's in order to get the longitudinal and the transverse part. And this will give you a relationship between S parallel and F and G and S perpendicular and F and G. And this, you can recast it in terms of this differential equation.
Involve some expansion, because otherwise why do you get a derivative in L? And does it involve some expansion?
No.
So why do you get a derivative in L, like from this computation?
I don't remember. I don't remember exactly.
Okay.
Derivative will come out. So certainly because you have to I don't remember exactly, but maybe you have to do some kind of backward engineering by computing the derivative, and you will see that the derivative is you can cast it this way, etc. So I don't remember the details. Anyway, that's not the most important relationship. The most important one is the next one, which this time is obtained through Navier-Stokes. So the idea is the following: is to write Navier-Stokes at one of the endpoints we are considering, multiply this Navier-Stokes at this point x plus L by the velocity at point x, and add to it Navier-Stokes at point x times the velocity at x plus L. So you see, you do this kind of cross manipulation. And what you get, so I mean, I will not redo the computation either because it's also quite complicated. I mean, quite involved, but I mean, but it's in many textbooks anyway. So what you get is what is called the Karman-Haworth relationship. So this Karman-Haworth relation is linking, so the second order structure function, the third order parallel structure function, so longitudinal structure function, and the dissipation. Okay, so this is an exact solution, exact consequence of Karman-Haworth. Plus, in that case, plus you have to use also isotropy and homogeneity. Okay, so now if in addition to being homogeneous and isotropic, we say that we are considering a developed turbulent flow which has stationary statistics. So stationary statistics, it means that this term is vanishing. Okay, and then developed turbulent flow, it means that there are some scales where this term is negligible. And then if you integrate this equation, so you see, in order to get rid of this derivative with respect to L, what you get is what is called Kolmogorov flow, which is telling you that the third order longitudinal structure function has to be proportional to epsilon L with a negative sign. Okay. So the assumption there are, in addition to isotropy homogeneity, are stationarity of the turbulent flow, the fact that you have steady state statistics, and the fact that you have an inertial range where terms of this kind can be neglected.
So why in the inertial range this derivative is negligible? Delta L and second order longitudinal structure function.
So this one is negligible because the inside the inertial range, this thing you can show that it's less than the constant, that it's decreasing. Okay, so basically this term will be negligible with respect to the term which is proportional to epsilon.
Okay, so it is negligible. Okay, so it is, so 4/5 epsilon L dominates over this term.
Exactly.
In the inertial range. Okay.
So, and you see now that what we get from this equation so the first thing that we get is that, so remember, this is a third order moment. Okay, so that you have a third order moment which is proportional to L, which means, morally speaking, that you expect the increment to be proportional to L to the 1/3, which is what we were getting from dimensional analysis. Okay, so this kind of relationship is favoring Kolmogorov 1941 law, and at the end, it was also derived. So this Kolmogorov 4/5 law was also derived by Kolmogorov the same year as when he proposed this phenomenology of turbulent flow. And actually, it's this relationship which told him that maybe that if there is a self-similar solution so if the turbulent flow is self-similar, then the exponent should be 1/3. Okay, so actually, I presented you the things in a reverse chronological manner. Okay, it's okay. So the problem is that this is the only exact relation that we have in turbulence. Yes. So the cascade is from Richardson. It's not Kolmogorov. So basically in 1941 there are two important papers by Kolmogorov. One where he's deriving this 4/5 relationship, and the other one where he's proposing this idea of scaling self-similar solutions, and being where he's proposed that epsilon is constant over all scales. Okay, but the two are connected somehow. They were written the same year anyway. So then the second thing that this equation is telling us is that basically you see the third order moment of this longitudinal structure function of this longitudinal increment is negative at all scales in the inertial range. So basically, which means that there is some skewness, okay, in the distribution of velocity increments. So that in order to reproduce properly the statistics, this skewness is really important. Okay, and this negative skewness, what does it mean? It means that so negative longitudinal velocity difference means two fluid elements which are approaching each other. Okay, and positive means that they go apart from each other. So it means that events where fluid elements are approaching are more violent than events where they move away from each other. And this you can understand it with hand waving arguments, because fluid elements which are approaching, they are carrying some energy, then they come together. Coming together, they dissipate something, which means that when then they move away, they have less energy. Okay, so basically this skewness is related to dissipation, and that's why you have the skewness proportional to epsilon here. And this is a hand waving way to interpret that. Okay.
So by
yes.
stationary.
Yes, but please use the microphone when you ask questions, because.
So by stationary, you mean stationary in a statistical sense?
Yes, exactly.
Okay.
Yes, in a statistical steady state. Yes.
I was curious, so where does the skewness come in? I mean, in the equation or in the assumptions? I mean, So this comes out from the calculation.
Yes,
But,
sure.
So is it inbuilt into the equation in some way, or?
But you see, so basically, if you look, so here, if you look at this part of the equation, so the part which are giving S3 is this guy, and epsilon is this guy. Okay. So now you recognize the various terms in Navier-Stokes more or less. So this is coming from DTU. This is coming from the nonlinear term U grad U. In this manipulation, you are getting rid of pressure, so pressure is out. And these two terms, which are proportional to nu, because epsilon is proportional to nu, are coming from the viscous term. Okay, so the skewness is coming from a balance between transfers, so quadratic term. So of course, when you multiply it by u, it's becoming a cubic term, and energy dissipation, which is negative. That's fine.
Jeremy, so what is the, maybe you already said, but what is S2 parallel? I mean, what does one know about that?
So S2 parallel?
Yeah.
So what's your question?
Like what, maybe you already said, but and what does one know about S2 parallel? Like just the second moment.
Yes.
So what does one know about, like how the scaling with L and so on?
So the scaling we don't know. We just know this relationship between transverse and parallel.
But we don't have any relation like this for S3.
No.
But what does one know about it? I mean,
about S2, nothing.
Nothing. Oh, really? Okay.
Nothing.
Okay.
Not even the scaling. But I will come back to that.
So also this relation, this isotropy.
Yes.
Like, are there similar relations at each order?
Of course.
So
No. They are not the same relation at each order. Because no. Because then for all higher orders, you have pressure which is entering the game. So it's just some kind. It's magical that here you get rid of pressure. But at any, so if you write, so for instance, if you could try to manipulate things by multiplying by u square, etc. So then the pressure term will still be present, and pressure we don't know how to handle it. So you can write formal relations. So for instance, you can write an equation which is linking fourth order structure functions and increments of pressure, but then you don't know what to say about increment of pressure. It's not close.
So the perpendicular one you cannot.
No, you cannot say anything.
Find the more. Okay, even at 3.
Yes, no, there is. My PhD advisor told me that I should not spend time trying to find a new relation where people have spent 50 years trying to do it. You see, so I think that there are some smart people who try to do it, and nobody arrived to anything closed. So there is no possible closure. So the thing is that yes, you can get relationship, but then it will involve pressure.
So for initially we talked about scale dependent velocities. Now for the statistical description, we go to velocity increments.
Yes.
Now here S3, this was like epsilon L, and the UL, we found out epsilon L to the power 1/3. So UL cube scales like epsilon L.
Exactly.
There's some like why the scale dependent velocity is similar to this third order structure function?
Because it's so this is what I was saying is that it's the two are linked through dimensional analysis first. Okay, so that basically the S3, if you want, S3 is like UL cube, dimensionally speaking. Okay, and the second thing is that it's in at least for p equal 2. So basically this S2 relates to the correlation function. Okay, and the correlation function is just the Fourier transform of the spectrum. Spectrum and correlation functions are Fourier transform of each other. So which means that you see for at least for p equal 2, you can have this formal equivalence between what's happening in Fourier space and what's happening in real space. Okay, and UL we interpreted it from time to time as the energy content at a given scale, thinking in terms of Fourier, or UL is an informal phenomenological thing anyway. Okay, so let me move on. So now, so I'm coming to your question about S2. Okay, so now let's try to understand a bit what we expect for any moment of the velocity increments. So let's first recast Kolmogorov theory. So Kolmogorov theory is telling us somehow that we expect the piece order structure function to scale like L to the power P over 3. Okay, so that's what this is answering your question somehow. And this is somehow also it's a consequence of the scaling form that you can write that is equivalent to Kolmogorov 1941 for the distributions of velocity increments. And now, so what is actually observed in actual turbulent data is that you have anomalous scaling, and that actually the piece order structure function is going like L to some power zeta p, and this zeta p is different from P over 3. So here I'm showing you some data. So all data from 96, recent data from 2018. So you see first that the data are not too much deviating from each other. So which means that at least exponents are not changing as a function of time. And the thing then that you see is here is the dashed line will correspond to having scaling exponents given by Kolmogorov 1941. Okay, so it will mean that basically the exponents are just a linear function of p, okay, with slope 1/3, and the actual measurements. So of course, when p equals 3, they all collapse to 1. So this is the consequence of this exact Forfeit law. But now, if you look at different moments, there is a deviation. So for p equal 2, it's not exactly 2/3. It's a bit above. Of course, it's very slight. It's just a small amount above, but it's above. It's not 2. It's not 2/3. And of course, the higher the moment, the stronger are the deviations that you observe. Okay. This is the fact. I mean, the data. And yes, needless to say that these two these two measurements are experimental measurements. That if you do numerical measurements, you get the same kind of results, maybe with larger error bars only. And that these two experiments are very different. So one is a wind tunnel. So you have a wind tunnel, you have a grid, and you measure something with your hot wire. And the other one is a von Karman flow. So von Karman flow, you remember, it's two counter-rotating fans, and you look at the flow in the middle. So here it's made with water, and the measurements here are done with PIV. So you see it's different measurements, different flow, different fluids, and you see that the exponents have this. So we have the idea that the exponents are universal.
So this for large L, right? This relations are for large L.
For large L.
L is you assume to be large separation.
So it's separation inside the inertial range. So separation larger than your viscous scale,
okay,
and smaller than the large scale of your flow.
Yeah. So I guess
it's intermediate.
So because of this only, you can a posteriori say that the term you neglected, that's valid basically, right? Because that's now the term which you neglected, that is del L of L to the power minus 2/3.
Yes, yes.
So that's smaller, you can say.
Yes, sure. So now I will try to tell you a bit about some ideas on how to describe these deviations. Okay.
So for p equal to 3, even the 4/5 is verified. Is it experimentally?
Yes, the 4/5 flow is yes. I forgot to say that at the end, this is also a way that experimentalists are using in order to measure epsilon. Okay, so if they have a good measurement of the third order structure function, okay, then they can this way estimate epsilon in experiments. Yes. So the mean rate of dissipation. So yes, so maybe first, so here there are some other results which are somehow confirming the fact that it's not self-similar. So here, what I'm showing are the marginal of the longitudinal increments, so the PDF of the longitudinal increment, okay, and for different values of the length at which you measure this increment. And so basically they were a bit shifted in order that you see that the shapes are different. So if you start with a very large value of the separation, so you have a distribution of the increment which is almost Gaussian. Okay, and when you decrease the length scale to approach the dissipative scale, this distribution is developing tails, okay, which are super exponential, which looks a bit like stretch exponential. Okay, and again, this is independent of, so this is yet another flow. It's an air jet. So you have a nozzle, you put air and you measure increments in the wake. And this is again the data from the wind tunnel in Modane. Okay. Yes.
Formally, the correlation functions can be computed from the underlying joint probability distribution, right? Psi.
Yes, sure.
So how is U perpendicular being marginalized over? Is it being integrated out, or are we fixing a particular value of U? I mean, is this
So
the conditional the probability distribution on U parallel, is it the conditional probability distribution or arrived at after marginalizing over?
So it's this thing you mean? Is it the conditional?
The previous slide.
The previous slide.
Yeah.
So what does this mean? What is your question?
So I mean that say supposing in the next slide one is computing higher order moments of del U parallel. Right?
Yes.
At least formally, they can be assumed to be coming from the joint probability distribution side that you wrote down.
Yes.
So, but how is that computation being? I mean, if we were to imagine that we can do such a computation, are we marginalizing over the U perpendicular?
Yes, exactly. Yes. It's a so when you look at that, for instance, you average over all possible value of delta U perpendicular. It's not a conditional average. Okay, so now basically from these measurements, it is clear that you don't have this kind of scaling behavior, which would be what you get from Kolmogorov 1941. So that's clear because you see that if you had this kind of scaling, then all these curves will be described by psi, by a unique function, and you see that you have different shapes. It's clear. Okay. And the second thing that you can measure is also the flatness, so the usual flatness, which is defined as the fourth order moments divided by the square of the second order moment. Okay, so what we know is that if the distribution is Gaussian, this number, this non-dimensional number, is equal to 3. Okay, so that's the typical result you get for the flatness, and basically the flatness is a way to measure deviations to a Gaussian distribution. So now, if you look at this flatness as a function of length scale, so now we start from large scale. So at large scale, so this point here, I don't know if you see it, it's 3. So you start from a flatness which is very close to 3, which means a distribution which is almost Gaussian. And then you decrease scale. Basically, it's going like a power law up to scales which are starting to be of the order of the dissipative scale, where it's then saturating to a finite value. Okay, and somehow this exponent minus 0.1. So if you think in terms of the scaling before, so here you see, so basically if you have a scaling like that, so flatness is nothing but L to the zeta 4 divided by L to the 2 zeta 2. Okay, so basically this exponent here is exactly zeta 4 minus 2 zeta 2. Okay, that's why we do observe this power law. Okay, so these are different measurements which are confirming the fact that we have anomalous scaling. Okay. So why? So now with the hand waving thing, so basically, why do we expect this anomalous scaling? So you remember that somehow the idea of Kolmogorov turbulence and of Richardson cascade was that you were injecting energy at large scale, and that this energy was flowing downscales up to the dissipative scale. Okay, and here what you see. So if you look at, so remember this is a slice of the energy dissipation. So what you see is that you see that you have regions which are dissipating more. You have regions which are whiter than the others. Yes.
So this previous one, you said for large L, it approaches Gaussian.
Yes.
But it's still skewed. Distribution is still skewed, right?
No, I think skewness is going to 0. So no.
Because
Skewness.
it always goes like epsilon L, no?
Yeah, but no, it's going to like epsilon L. So let me go back to that. So here I neglected the term, which is the forcing term. Okay. So if you put forcing at large case,
okay.
Basically here you will have an extra term which is coming from forcing.
Okay.
And so now, if we assume to be in this intermediate range, both we can neglect this term, but having L, the separation much less than this capital L means that we can neglect forcing. So I was a bit sloppy on that. I didn't write the effect of forcing, but forcing, the presence of forcing is killing this thing.
In this range is L to the power 0.1 or something, is it? That this range, when you look at the next.
So
yeah,
sure,
so
yes.
L to
So
the
basically, you see, so maybe in these simulations, a capital L will be between 1,000 and 10,000. Okay, this.
Okay.
Okay, in these units. And so you need to be much smaller than this capital L, much larger than eta, in order to see this intermediate range with scaling. Okay.
And this is where this other law is valid.
Exactly. So now what I wanted to argue is the following: is that if you look at the spatial organization of dissipation, you see by eye that things are not. I mean, you don't have a gray image. Okay, so you don't have dissipation everywhere. You have places with almost no dissipation and places with a lot of dissipation. Also, I didn't say, but the color scale here is log. Okay, so basically it's really emphasizing. I mean, if I wanted putting log, basically I will see only the very large values popping out. And now if you zoom, so let's assume that you zoom in a given place. What you see is that somehow, again, at smaller scales, you have different fluctuations of dissipation. You have places which are more white, like this one or this one, and places which are black with no dissipation. And again, if you zoom again, you see again the same kind of structure. So which means that somehow you can think that indeed you have a cascade of energy up to smaller and smaller scales where it's dissipated. But in this cascade, you have only some places which are peaked. Okay, and this is the idea of what we call an intermittent cascade. So intermittent cascade. So you remember the idea of Richardson, that you inject energy, you dissipate it. So you inject it at the large scale, you dissipate it at scale, at the Kolmogorov scale. And now, so basically, what we had before was that we had almost like a tree to put in energy downscale. But now assume that it's like a tree, but you just randomly select some branches of this tree. Okay, so for instance, this AD will not give energy to these three guys, but only to these two. So this one is empty. Okay, so and this in the picture before will correspond to a black area in our flow. Okay, it's okay. So this idea actually is also due to Kolmogorov, the idea of intermittent cascade. So this is now Kolmogorov 1962. So it's 21 years after his first work on turbulence. And so the idea now is to say, okay, so let's try to formalize it a bit, so to make a toy model for this, not to formalize, rather to make a toy model for this intermittent cascade. So assume that you have some epsilon at a given scale, and that you need to transfer this rate to smaller scales. But you do it not in a uniform manner, but you do it by picking randomly how much you put in each of the sub boxes that you have. So assume that so we divide our spatial cascade in different steps. At each step n, we have a scale, a given scale, which is a large scale divided by 2 to the n. Okay, so each time we cut in 2 our domain. And then, so which means that at a given scale L, the energy that you have to transfer to smaller scale is a product of different factors, which are coming through the different scales, times the energy you had at the beginning. Okay, so it's a cascade, a Kolmogorov cascade, actually. So now, so basically, so is this clear? So each time you, so let me maybe make another sketch. 1D sketch will be easier. So you start from some epsilon I here. Okay. So then you cut in 2 pieces. To this one, you transfer lambda 1 epsilon I, and to this one, so of course you need to have you need to conserve something. So to this one, you transfer 1 minus lambda I. Okay. And then you repeat that. So to this guy, extra here each time. So now this will be lambda 2, this will be lambda 2 prime, or 1 minus lambda 2. This one will be lambda 2 prime, and this one 1 minus lambda 2 prime. Okay, and you continue that up to the smaller scale. Okay, so now if you look at one box here, what you will get as an energy to transfer is lambda 1 epsilon I times lambda 2 times lambda 3. So, and this is what I wrote here.
So earlier energy was evenly distributed. Now it's like randomly distributed.
Exactly. So just assume it's randomly distributed. And what you assume is that the different, so at the end, it means that it's a multiplicative cascade. Okay, so that it's basically the proper thing to look at is the logarithm of the energy transfer. Why? Because when you take the log of this thing, you're transforming this product in a sum, so it makes things a bit easier to tackle. And then if you assume that the various factors at each scale are independent processes, random processes, then you have here a sum of independent processes. So you can apply central limit theorem. And what you get is that the logarithm of this guy is a Gaussian. Okay, so that's the very simple Kolmogorov 1962 scenario. Okay, so log of dissipation Gaussian, it means that dissipation is log normal. That's what we call a log normal distribution. And typically it means that the probability, that basically you need to think about the dissipation in terms of some power of the scale. Okay, so that basically, if you want, it's this x here, which is becoming the relevant parameter. Okay, so this is like, so this x is like log of epsilon divided by log of L. Okay, and this x here is, so in this very simple case, it's a Gaussian, but in principle, you can think that it's obeying some kind of large deviation principle. Okay, so that it has a distribution S, which so basically that its probability distribution has such a form, like exponential minus n being the number of steps that we have to do, times a rate function which depends only on this x. Okay, so this is typically what we can guess from this intermittent cascade model. Okay. So in this very specific example, so basically you can write exactly S of x. S of x is a Gaussian like this, with a parameter mu, and mu is the mean of this log in basis 2 of the transfer, of the transfer factor. So what I've shown here is actually the probability distribution function of this log of epsilon. Okay, and what you see here, so it's the blue curve is our numerical measurements, and the dashed line is a Gaussian. So what you see is that indeed, if we look at either deviations close to the maximum or the tail of very large dissipations, that indeed we are very close to a Gaussian. And of course, the only place where we have deviations is the left-hand side, so which means that it's places where epsilon is less than the average. Okay, so it's places which are the calm places of the flow, the calm regions of the flow. Where epsilon is the black regions I was showing you. And so these deviations could be due to the fact that, for instance, that n is not large enough, because n could depend on the region of your flow. See, so here we have cut each time in 2 pieces, but at the end you could think that you have to cut in pieces which depends on the amplitude of your fluctuations. So in places which are calm, it could be that you are already reaching eta at this place. So I will come back to this fluctuating eta later. Okay, so do you have questions about that? Yes, please.
How is this exponent x related to the 1/3 exponent that you had previously? There also, at least at the typical part, it was Gaussian only.
So you're willing to relate these distributions to the exponents?
To, yeah, like the side distribution, scaling distribution you had.
To the scaling of the statistical function? That's, I think it's next slide. No. Yes, it's there. I will come to it. So you had those other questions?
Yeah. So this so epsilon L is the energy transferred at the scale L.
Exactly.
Right.
But locally.
Locally, which is much larger than eta, but much smaller than
Exactly.
L.
Exactly.
And then earlier we said that this at those stages, basically there is no dissipation; it only transfers the energy. So epsilon L should be independent of L.
So epsilon L independent of L is the idea of the normal cascade.
Normal cascade. Now somehow.
So now somehow you make things intermittent in the sense that you choose a rate. So you have a non-dimensional parameter.
Yeah.
So in average, of course, everything should average to 1, to the same epsilon.
Yes, but here we are somehow assuming that epsilon L depends on L.
Yes, yes. That the statistics of epsilon L depends on L.
Depends on L.
Yes.
So, okay. So the mean is still independent of
Exactly,
L,
exactly.
But now we are just looking at the fluctuation.
Exactly,
and
exactly.
That depends on L.
Exactly, exactly. And if you want, so now and the idea is to treat the fact that you go down the cascade as a process on which you can compute some large deviations. So the mean should be the mean of epsilon, but then you have fluctuations that are controlled by such a large deviation. So there is another way to interpret this, which is through this multifractal formalism. So let me explain. So now what we assume now is that for a given scale L, okay, so epsilon L, where did I define it? I did not define it actually. I'm sorry, I should have defined it. I'm sorry? Exactly. So basically, what I call epsilon L is the average. So assume that I take a cube or a box of size L in my flow. And so here basically I'm just coarse graining the local value of the dissipation. So here I have some epsilon local, which is defined as so this nu by 2 times the write it this way, the norm of the symmetric parts of the gradient tensor. Okay, so this epsilon L is nothing but 1 over L cubed. So this, of course, local means that it depends on x and time. And so this epsilon L is nothing but so the integral over my domain over my cube of this local value of epsilon. Okay, that's okay. So I'm doing a coarse graining of the dissipation. So now what these multifractal ideas are telling us, so now we are jumping to 1985, is they are saying that we can consider that locally at a given position, this coarse grain dissipation so is nothing but the mean dissipation times a dependence on the scale with a given exponent. And this exponent has a local value. Okay, so you have places where alpha is having a given value and other places where alpha has another value. And what we say is that this is true on a set for which you have a given dimension f of alpha. So this is multifractality, exactly. That's how we define multifractality. So this f of alpha is what we call the fractal spectrum. So let me give you some examples. So for instance, if we have f equal to 0, okay, so which means that it's a dimension equal to 0, so which means that we are on the point like that, and it could be that on this point, so with this probability given by L to the power 3, okay, so to be on this point, so what we get is a given exponent alpha like this. In that case, f of alpha will be 0. And then if f is 1, it's as if we were on a line. F is 2 is as if we were on a surface. But in principle, f can take any value here. Okay, so now what we say is that the probability of seeing a given exponent alpha here will be just L to the power of the codimension, so 3 minus f of alpha. Okay, so f, we don't know it. And now this we can recast it in terms of distribution of epsilon of the coarse grain dissipation by saying that the probability to observe a given value of the dissipation is itself proportional to a power of L, which depends on alpha, alpha being related to the dissipation through this thing. Okay, is it clear? Did I lose you?
If alpha is defined locally.
Yes. Alpha is defined locally. Alpha is fluctuating.
So this is the distribution of P of alpha is the distribution of alpha.
Yes, the distribution of alpha at a given scale L behave this way. So that's what it means to be on a fractal set. Okay. So so the exponent alpha, you see it on a set which has dimension f of alpha.
But f of alpha is a given function. No,
f of alpha is a given function. Yes.
Function. Okay.
So if you want, it's a kind of a generalization of scale invariance. Okay, so now instead of saying that I always have epsilon constant, okay, which will mean alpha equal to 0 everywhere, or instead of saying that epsilon L is going to some L to some fixed power, what I do is that I allow this power to fluctuate. And this power is fluctuating in such a way that it has also some scaling property. The probability to locally see a given alpha at a given scale has this dependence on both alpha and scale. See, so it's a kind of generalized scaling form. Okay. Maybe I can try to sketch some example. So assume that, what we started with in this idea of Richardson cascade was to put the same dissipation everywhere. You agree? So now what we can decide to do is to put dissipation only at given points. Okay? So which means that if we take a given scale L, okay, as it's a point, the probability that at this scale L, I am indeed intersecting a point is, so the probability that epsilon is different from 0, so epsilon is 0 everywhere, and here epsilon has a given value. Put it E, okay? So the probability that epsilon is equal to E, or is larger than E, if you want, in my box, will be going like the size of my box to the power 3. You agree with that? So it's a 2D sketch, but I'm in a 3D space. Okay, so with the probability proportional to that, I have epsilon equal to E. And then I have nothing elsewhere. Okay. So now let me complicate it a bit. So in addition to the points, I can add lines. Okay, on these lines. So these lines, they have typically a length lambda, let's say. And on these lines, I will say that I have epsilon equal to, I don't know, E divided by lambda or something like this. Or E1, let's just put E1. Okay, so now, so this was the probability to have epsilon equal to E, or less. And now the probability that you have epsilon equal to E1 will be like L to the L now to the power 2. Because I mean, it's easier to meet a line. Okay. So now, so this is the first ingredient, the fact that you are living on a fractal set. But now, the next thing is to say how this E and E1 are depending themselves on the scale. Okay, and so now the thing is that somehow you say that capital E will be itself something which is like L by L to some power alpha 1. So for instance, if it's points, you could imagine that you have many points like that. So I mean, this dependence on alpha 1, on L here, through alpha 1, will tell you that when you make the box smaller or bigger, the number of dissipative points you have there is decreasing or increasing. So it will decrease or increase the dissipation. And same, so same on the line. Now you're on the line, so you have this E1, which will be L by L to the power alpha 2. I'm sorry about the notations. So let me call this E1, 1, 2, 2, 1, 2. Okay, does this sketch make things a bit clearer? So basically, this is just you can see that. So basically, there is no proof that this is the proper way to. I mean, there is no proof from basic principles that turbulence statistics are obeying this thing. But this is just, you can see this just as a generalization of the scaling of a scaling form for the distribution. And typically. Basically, it's making a more complicated dependence on scale compared to something which is just pure scaling as we had for Kolmogorov similarity. So now the Kolmogorov similarities, there is one way to recover it. Yes, please.
So here f is a function of alpha and alpha itself is a function of x.
Yes.
So yeah, I can see that, we always have this freedom of multiplying by L over L because it's dimensionless.
Yes.
Raising to a power of alpha. But what happens to homogeneity if is the turbulence still homogeneous because now different points in the fluid dissipate energy at different.
Yeah, because the homogeneity just means that all these statistics are independent of the position. Okay, so that at the same position you have always the same distribution. At any position, yeah. So okay, so now how to recover Kolmogorov 1941? So it's pretty simple in the sense that if you assume that this function, so this fractal spectrum, is 3 for all alpha equal to 0. So alpha equal to 0, you see it means that epsilon n is the same epsilon everywhere. And you say that having epsilon l equal to epsilon is space filling. So it's for this alpha equal to 0, you have 3. Okay, and then for all other values, I'm sorry, it's alpha different from 0. So for all other values of alpha, you have minus infinity. So which means that dimension minus infinity means that's something that you never see. Okay, so now you see if you assume that, basically this is exactly like assuming Kolmogorov 1941. Okay. So now if we turn back to the structure functions, which were the thing that we were willing to understand from the beginning. So now we do the following thing. So this is using what is called Kolmogorov refined self-similarity, but never mind. So what you do is the following thing, is to say that now if I want to compute the piece order structure function at a given scale L, and by dimensional analysis, locally, it will be like the local dissipation times L to the power P over 3. Okay. So locally, you expect to have something where, so you remember that we had this idea that the velocity at a given scale L is like epsilon times L to the 1/3. So what you do is that you apply this kind of dimensional argument locally at any on a box of size L where epsilon could be fluctuating. Okay, so that's why you have that the piece order moment of the velocity will be like epsilon L to the P by 3. So now in this average, you plug this distribution for epsilon. So you make epsilon fluctuate. Okay, so basically you have a part here which is coming out, which is just the dimensional way to think about this quantity. And then here you have a sum, an integral of all possible values of your singularity exponent alpha times a power law of L, which depends on alpha and p. Okay, so now how do you treat that? So basically now, so you have a sum of alpha of different power laws. So you make a saddle point. Okay, so you take so L is much smaller than capital L, so which means that this is a small number. So you need to pick up the smallest power. Okay, so you pick the smallest power, and this will give you the anomalous exponent, the intermittent exponent, as so the infimum of all alphas, you see, of this guy here. So there is a relationship between this spectrum, dimension spectrum, and the scaling exponent, which is just through a Legendre transform. So you see it's a Legendre transform because somehow here you have p times alpha minus f. Okay, so and you take an infimum. So the scaling exponents and the dimension spectrum are just related by Legendre transforms. And dimensionally, this is how the thing is taking as the form. So basically, the longitudinal circular function is going like so. This is the dimensional expectation, which is coming from so that we are getting through Kolmogorov theory, from Kolmogorov 1941, times what we call an intermittent correction here, which depends on the, as a power law, on the ratio between the observation scale and the large scale. Okay. So what does it mean in the language we were using yesterday? So yesterday we were saying that dimensional analysis is good. We can get everything through out of it, etc. Because we could get all the exponents, all the scaling behavior, etc. So now what we were saying before was that inside the inertial range, quantities were depending only on epsilon, on the mean dissipation rate, and on the length scale. Okay, so now through that we see that there is still a dependence on the large scale, which is not disappearing.
So zeta 3 is equal to 1/3, or
and zeta 3 is equal to 1/3.
that you can see.
No, this is giving you some constraint on f. I will come to that. Okay, so it's just a way to represent statistics. Okay, just something a bit more complicated than the scaling form.
So in this saddle point calculation, this Jacobian term is not important.
Which term?
Rho.
Yes, rho is the distribution over alpha is not important. It's just a function of alpha, which is supposed to be independent of scale. So it will just put a different constant there. So next step is let's go back to the log normal model. Okay. Yes.
The previous slide. So this form of epsilon L. So the distribution comes in alpha.
Yes. Exactly.
So now this also should give the log distribution for the energies. Does that?
So if you want, you can write it this way. You can write that your so maybe it will be easier to make some parallel between typical large deviations. In which I assume that my quantity, the quantity I want to look at, is a sum. So let me define y as a sum of some variables. Okay. Okay. And here basically, so yes, maybe I will need to. It's better to normalize it. Okay. And then here, the parallel is this epsilon L. It's not epsilon L, it's log of epsilon L. Log of epsilon L divided by log of L. That's right. I mean, from the what I was having before. It was something like this. Log of epsilon was a sum of independent variables. And basically, now if I divide by n is nothing but the log of the see, through that, n is the log of L. Here. And so now here, what you expect is to have, so n, so here, n is log of L, okay? So now if what you expect in a large deviation is to have that P of y at a given n will go like exponential minus n times some function which depends on y. Okay? You agree that that's fine? And now here, so now here, this is what we call alpha. Okay, and what we say is that P of alpha is like exponential minus n, so n is log of L. I'm sorry. N is minus log of L. Because L is going to 0. Okay, so it's a negative number. Log of L is a negative number, so it's actually minus, times some function, so that I will call h of alpha. Okay, that's fine. So this means that epsilon is like L to the alpha. And this means that P of alpha is like, so I have log of L, so it's some L to the h of alpha. That's okay? This was useful? Not necessarily. So thinking, yes.
Alpha is like the sum of log lambdas in the previous one, basically, right? In
So
the previous picture,
alpha is what you observe at a given.
yeah, and then
L.
that's in the previous picture, this cascade picture, that's like the sum over log alpha.
And the cascade picture is giving you the fact that this thing is a large parameter, and that basically you have this maybe multiplicative or other kind of process going down the cascade. So of course, if it's a multiplicative cascade, then you have exactly this kind of picture. Okay, so let me so let's go back to go back to your questions about constraints on this f of alpha. So let us take this simple example of something where this so 3 minus f of alpha, which is like this h of alpha. Let's assume that it's just a quadratic function. Okay, so we just assume that it's a parabola. And from the formula that we had to relate the scaling exponents, so basically we are getting this thing here, okay? And now we have actually two constraints. So there is a first constraint, which is the fact that the scaling exponent of order 0, okay, so which is something to the power 0, should be 1. So the scaling exponent should be 0. And this is telling us that we have to have this equal to 0. So which means that so having this equal to 0 in a quadratic function like that means that the root is a double root, okay, has a multiplicity 2. What it means that the discriminant is 0. Okay, so which means that the minimum has to be attained at 0. Okay. And now the next step, which is to impose that the third order exponent is 1. Okay, so then again we have this formula. We do some algebra and we find that it means that b should be -1/2, and this is to be consistent with this 4/5 law. And then this means that this form here actually has to be like that. Okay. And having a form like that means that basically, so usually it means that there is a single parameter, this capital A, which is usually recast this way by introducing this mu, which is just this 1/4A. And so that's, and this mu parameter is usually called the intermittency parameter of our distribution of velocities. And so now you see that the spectrum, I mean the fractal, I mean the dimension spectrum of our distribution is taking this very simple form, which depends on the single parameter. Okay, so if we have a log normal distribution, so if we take a parabola for our large deviation form, then what we get is this formula with a single parameter.
I guess
okay.
A priori you don't have any reason to stop at alpha square, right? Suppose I do
No, you can go to a higher
order,
yes, yes.
then you
it
have
should be
more
convex. That's
more
no,
parameters.
you can put more parameters. Yes. So now the thing is that maybe it's not very useful to put more parameters. So these are data. So now let me assume that I want to have this form here. And so here what I show is from numerical simulations, I'm showing an estimate of this 3 minus f of alpha that I obtained by looking at the logarithm of the distribution of alpha divided by the logarithm of the length. Okay, so basically I have this thing, okay? So I just take log of p of alpha divided by log of L, okay? And this, in principle, this should be like h of alpha. And what you see here, you see that different colors here are corresponding to different scales. And so then the dashed line which is shown there is indeed this log normal model with mu equal to 0.1. So this intermittency parameter equal to 0.1. And what you see is that it seems to be pretty good at negative values of alpha, but at very large values, it's not that good. Okay. So again, small values. So remember, this I can edit. Small values of alpha. Let me write it here. So remember, I have this thing. So small value of alpha. So L by L is small. So small value of alpha means that this is big. So which means that if I look at alpha negatives, I'm looking at places where I'm dissipating more than the average. And so which means that the place where things are pretty well collapsing corresponds to violent places in the flow, where you have more dissipation. And alpha positive on the reverse corresponds to places, or to these calm places, for which maybe this idea of cascade is not working very well, as I already mentioned. So now there is another measurement which one can do, which is now the variance of the logarithm of epsilon at a given scale as a function of log of L. Okay, and so if we were log normal, everything should collapse on a line. So you see, it's not that bad. It's okay. And so collapsing on a line, which means that the variance of the logarithm of epsilon is like log. Okay, and this corresponds to the fact that this is entering the class of what we call log correlated processes. Okay, so so the variance of the log of this epsilon L so epsilon L is coarse grain. So if you take the variance, see it's a square of an integral, so it's something like this. So you remember epsilon L was a coarse grain value of the local epsilon. If we take this square, it means that it's as if we were integrating the correlation of epsilon. Okay, you agree? So the average of that will be something like, it will be proportional to the integral of epsilon of x, epsilon of x prime, of x plus r, T3R, sorry. It will be proportional to something like that. So which means that here, this quantity here is actually like an integral of a correlation. And the fact that it's going linearly as a function of log means that this process, the local value of epsilon, is very close to what we call a log correlated process. And then there is some backward engineering that one can do, is that for log correlated process, one can show that when you coarse grain them, you get a log normal distribution. Okay, so which means that things are consistent. Yes.
Is it possible to check what happens for the higher values of T when things are not matching with the
Yes, so I have it here. So now that we have some value for f, so as we were saying, so we can use this log normal model, and so we can get some explicit formula as a function of our intermittency parameter mu for the scaling exponent here, that we can compare to data. Yes.
mu was the parameter that characterized this f alpha function.
Mu is the intermittency parameter. That is, so basically mu is this thing here, this intermittency parameter, which is the only parameter that we have in our log normal. Okay, and here the base value that was the best fitting the data is this mu 0.1. Okay, and now here again, so these are the scaling exponents, so it's the same figure as before. So the Kolmogorov 1941 prediction, and now the dashed line here. The bold dash line, not the thin one, is this thing again with mu 0.1. Okay, so and you see that it's pretty well fitting the data, and it's indeed predicting that you have very small deviations at small values of p. So now there are some problems with this log. So it seems okay, but there are some problems, of course. So the first problem is that when you see this formula, if you go to p to infinity, you see that the exponents are becoming negative. Okay, so the dominant term would be this minus p squared. So actually, all the zeta p's are becoming negative for p bigger than this value. Okay, so having negative exponents is not possible because it will mean that when you go downscale, your moments are increasing, okay, instead of decreasing. So which will mean that certainly there are some moments which are diverging. And in addition, this means that it's violating the conservative character of the cascade in the sense that you remember in this idea of a cascade, we were deciding to put something there, something there, something there. And then we had a constraint that the sum of all what we were putting was exactly what we had at the scale above. Okay, so this constraint is violated by the log normal distribution. And then, of course, there are many other models Which
So this one, taking this F alpha to quadratic, right?
yes,
So in principle, you can take the higher order.
exactly, exactly.
Okay.
So you can take higher order. So of course it has to be convex, but you can take higher order extra. But then there is another problem. But the problem is that if you take higher order, then it's hard to match it to some phenomenological cascade picture. See, so the quadratic you understand because it just means that you have this multiplicative coefficients which are independent from each other. So no, it has things to do. So basically, this number here is the same as f of alpha. It can have tail, yes, indeed. It can go, yeah. It can be linear. It has to stay convex, but it can be linear. Yes, exactly. Yes. So anyway, so I don't want to go into the details about the different other multifractal models, but there are other models which are usually mumbling some physical arguments. Okay, so there is some random cascade models which are a bit more elaborated than what I told you. Then there are some models which are more based on Poisson statistics of epsilon, etc. And they give different rate functions. Okay. But you see, in order to distinguish between them, one really need to go maybe to much higher order statistics for which we have no data. So it's anyway, I mean, any of them is doing a good job if up to order 10, you see. So that's it's okay.
So it stops at 1994 theory.
Yes. Yes. Now people are using the theory to understand other things, but not trying. No, there is a paper by Ruel where he has yet another model. I could have had Ruel 2020 or something like this. So anyway, so now I wanted to move a bit to other kinds of intermittency and consequences of intermittency on other statistics than just the short-term functions. So I have 2 minutes. So the first thing is so for instance there is one thing on which people have been excited a lot, which is coming from the possibility to make particle tracking measurements. So now you are tracking particles in your flow. So which means that basically you are following tracers of the flow like that. And now you can measure the velocity of these tracers at different times. And then people started to look at the statistics of the increment of velocity along these tracers, And again, so you can define now what is called Lagrangian structure functions. And defined as usual as the piece order moment of the increment of velocity over a given time lag this time. So now it's a time, it's not a scale. And then there is a supposed equivalent of the Forfy flow, which is not shown actually, but which is involving the same kind of scaling, which this time is applying to the second order moment, where you expect the second order moment to go like epsilon times tau. Okay. And now, so of course there is no proof, but and actually what the measurements are showing is that again these things have some anomalous scaling behavior. So with some exponents which are not given by Kolmogorov 1941, and using multifractal model, one can get some predictions. And this I will talk about it in the tutorial. Okay. And then there are other kind of temporal intermittency. So for instance, again, I'm now still sitting along a tracer, but this time I'm measuring epsilon along this tracer. Okay, I'm measuring the local value of my dissipation rate. And this is typically the signal one is getting. So this is epsilon in units of the mean. Okay, so which means that this curve is averaging to 1. And what you see is that, what is clear is that you have bursts of dissipation, which are followed by very calm moments, and then burst again, extra. And the typical, and this time here, just to show you the units, is the large scale time. So which means that you see that correlation can be very, very long. So you can be for times which are of the order of the large eddy turnover time in a calm region. And then you jump in an excited region where you have very strong fluctuations. So you see, this is, one cannot say that this is not intermittent. I guess that's this curve can be an example of an intermittent curve. And so now how this is explained? So this is explained typically by the fact that the trajectories from time to time, so they are most of the time they can be in very calm regions, so they're just following the flow on very large scales. And from time to time, they can be trapped in a very strong region, which corresponds to a vortex filament, in which they are trapped, and then they have a very excited motion. They dissipate a lot of energy before, and this is typically what's happening maybe here, before exiting it again. And this trapping can last very long. I'm looking at the dissipation at the location of a particle. So it's always epsilon. So yes, so in my flow I have a field of epsilon, and then my tracer, I'm measuring epsilon at the location of my tracer as a function of time. Okay. Exactly. I'm still measuring the energy dissipation in the fluid. And typically, you see, this is the kind of autocorrelation that you're getting. So the blue one is the dissipation, the red one is the entropy. So it's another measure of the gradient, but this time of the rotational part of the gradient. So dissipation is somehow the norm of the symmetric part of the velocity gradient. Remember, it's a norm square of gradu plus gradu transposed, and entropy is the same thing, but for the antisymmetric part. Okay. So now what you see is that things are correlated over very, very long times. So typically, so this time is in units of the Kolmogorov time, of the smallest time scale that we have in the flow. This dashed line here, so that there is a tau L which disappears, corresponds to the large eddy turnover time. And what you see is that so in somewhere here you're expected to have some inertial range, and what you do see is that things are getting correlated, and the correlation is decreasing very slowly inside this inertial range, with a slope which could be -1, for instance, so which means that maybe long range, or maybe log correlated again, and for both quantities, which means that even if you look at a small scale quantity like a gradient, epsilon, entropy, you measure it along tracers, then it's getting correlated over very, very long time scales, for which you are expecting things to get uncorrelated pretty fast. Okay, I will stop here.
What was the time scale there?
I'm sorry.
What was the time scale you said?
So this thing is the large scale time. Yeah, it's this L divided by capital U. See, it's the large scale, the larger scale you can get. Exactly. I'm still integrating Navier-Stokes. And then inside my domain, I put solutions to the equation for tracers, to this equation that I treat as ODEs. So here I have the PD for U. Then I put many tracers which are each of them is solving that. Okay, and then I do statistics along the trajectories of these guys. Okay, but tomorrow is dedicated to Lagrangian things, so I will talk about Lagrange. Exactly, it's as if I was following a fluid element. Exactly, exactly. So basically, this means that I'm following the flow somehow. So following the flow, that's why I'm getting these very long time correlations. If I was sitting without following the flow, so sitting somewhere, of course, the correlation will decrease very fast. Okay, so thanks.